Anyone else who wants additional points for their midterm grade? Yes, no, going once, going twice. I guess nobody wants. Anyway,
The ceiling height, sir.
ceiling height, yes.
3 meters.
Ceiling height. Where's my blue pen? Keeps like moving around.
Is it 3 meters, sir?
No.
2.7, sir.
2.7 to 2.8 is the minimum. Um, you can go higher. So I'm looking for minimum. 2.7 is really kind of, I'll give Dara over here +1. Did you, who like use their microphone?
Tubin, sir.
Tubin, okay. Okay, what did, okay, you already know the number, so I'll include you as a +1 as well. Okay. Sige. Trisha Tubin, and that's Dara Tingal. Okay. Nice. So it's around 2.7. This is also applied everywhere. Even in Sydney, we had 2.7. So the reason for that is so the the ceilings don't get too low, but at the same time, the reason why there's a chance that the ceilings will get low is because that's where the utilities are in most buildings. There was a blue pen. I don't know where it went. I was just holding it. Anyway, it's over here. So in most buildings, the utility systems, there we go. The utility systems are over here in the ceiling, between the slab and the ceiling. So this is your concrete slab or your structural slab over here. You can see the beams. This is an I-beam all the way down there. This is your structural slab. And they're different sort of like beam supports or like joists. Okay. And then over here is your ceiling. So typically, like when I was in first year, I just thought the ceiling and the floor slab were the same thing, but they're two different things. And really, the purpose of a ceiling usually is to hide these like mechanical ducts and systems. So this over here, I'll just color it pink, is clearly an what do you call this? A duct, usually for air conditioning. This is how big they are. They're around like let's say zero point 0.2 to zero point 0.3 in depth. Let's say zero point 0.4. And then width, they can range anywhere from like zero point 0.6 to 1 meter. And then over here are more like ducting. I think this is also for like air conditioning or something like that. Pipes are a lot smaller. Or maybe they're bunched up together in these like cases. Because another way to like secure pipes is to encase them in kanisha in ani. So there could be like pipes in here, like sanitary and water supply pipes, just to decrease the chance of leaking. Because if you have just an exposed pipe over here, and then let's say it's a water supply pipe and it leaks, it goes into the roof, and then that damages the roof, and then you can like that will be like a whole thing to fix. So maybe it's placed inside these steel cases, or like it could be PVC as well, and a lot of different other materials. It's lagging. Photoshop was lagging for some reason. Also notice the beams go all throughout. Okay, that's how you know they're structural beams, structural elements. So beams go all the way from here to like here, and then there's another set of beams intersecting at this column and going that way. Also notice the thickness of the column. So you see that's a person there. I don't know why, what the heck, why is it lagging? Let me just close all tabs. Must be being weird because of all the tabs. How big is this image? Image size. It's not that big. It's only like 72 dpi. So you see this is a column over here and a person is like this. Oh, it's really lagging. What is causing this lag? could be my camera. Wait, let me just turn off my camera, see if that helps. What is causing this lag? The screen share? Anyway. Okay. So I have a person over here. He's about 500 to 600. Let's just say 600 mm wide. So definitely this column is around the 1 meter to like 1.5 meter thickness. So that's how big this thing is. And notice the spacing can't be more than, let's say, like 10 to 12 meters. So if that's 600 person over there, you can fit like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So calculator, 15 times zero point 0.6. Yeah, so about 9 meters. So definitely 10 to 12, depending on like the perspective. So that's how big your column should be. So when you design your schools, make sure that the span reflects in your columns, or the column reflects the span. So if you have a span of 10 meters, very obviously your column should be about 1 meter thick. Okay. And then let's go back to the mechanical systems over here. So these spaces, or this space between the beams and the ceiling, is where your ducting and piping would be. How big the ducting and piping are depend on the amount of utilities in your building. So centralized air conditioning systems typically look like this. Let's say I would guess this is zero point 0.4 actually. 0. Let's see, that's 600. Yeah, it's almost as wide as a person. So maybe that's like I think very easily 0. 0.6, and this is very easily like 1 to 1.2. Someone is making noise in front of my house, out of the room. Someone's like banging the door for some reason. And then again, the utility system can be included between the ceiling of your like roof, like the what not roof, but like the roof area. Notice this sort of paneling here. This ceiling material is covering this. I think this would be more electrical systems, because there are a lot of lights over here. And then notice this gutter over here for the roof. So the water flows in here, and this should have an angle that should be going somewhere. And this should be like pipes, electrical wiring are usually included in like orange PVC pipes, or dark orange PVC pipes, or was it waste was the dark orange? Either of those. Okay, and then you see the different timber materials being shown here. So this is a very good example showing the different elements of a building, and maybe you won't get a chance to visit it, but the Arc Daily article is always like here for you guys to like virtually visit it. Someone is still banging the door in front. I don't know why. Okay, so I'll just put this in our chat. So let's say we need to do a mechanical system for a house. I'm not going to do a school because like that's your plate. That's something you need to research. But it's pretty much the same principle. So let me just redraw the house over here. Like God's the banging stopped. And let's just make that on a new layer. So this is one thing that's kind of like lacking with architect Alino's like section over here. So he decided not to show probably to save time, not to show the different elements, the slabs and the ceiling. So let me try to like estimate where the slabs are. And this is the ceiling. So the slabs would be here. Let's zoom in a bit. The slabs would definitely be here, sort of on top of the grade, the natural grade line. Notice as well on the balcony, there's a dip in the slab. That's to prevent water leaking into the building. Okay, so the slab would be, I think, about this thick, because this we're pretty like zoomed in, and then the ceiling would be, so that's the slab over there. The ceiling would be like over here, just a little bit. Alright. I'll just exaggerate it so you guys can tell the difference. Ceiling over there, ceiling over here, and then ceiling over here. Mhm. I think some of the parts, like, I don't know why it's lagging. There it goes. Could it be the ruler? Let me turn off the ruler. Some of the rooms in this house have like a coffered ceiling, something like that. Like in the bigger rooms, you can see here, toilet over there. This is another coffered ceiling. Coffered ceiling. These are all ceilings over here. The beams would probably be, most likely be, like up here, like that. Okay, this is really like too small. Let me just do a quick blow up. So let's say this is your slab over here. You have a column like this. Dang it, I can't draw a straight line. Now I'll just use a break line to like separate the height. So you can do that. And then I'll draw the floor slab over here. This could be a beam slab. And let's say this area has a toilet. So there would be a dip in the slab, a depression on the slab. And then let's say this is a like a wall over here. Cannot draw a straight line today. Okay. Beam is too big. Beam is like that. And you can have your ceiling over here. Ceiling over there, and then another ceiling. That's exaggerating it so you guys can imagine where the pipes would go. And then over here, the roof structure, usually like steel or something. You would have the truss like that. And then it'd have like different sections. But web members, I think, is what it's called. Something like that. And it goes, if we zoom out a bit, say the apex of the ceiling is like somewhere over, this apex of the roof is somewhere over there. And then usually you have web members that look like this. And you don't need one here. So it's like, and you have like sort of the ceiling for the roof eaves. Functions kind of like a ceiling, something like that. And then it would have like some gutter over here, something like that. And then of course you would have your window somewhere over here. And let's say it's like a floor to ceiling windows. So the window jamb is usually represented by a rectangle. And the glass material itself would be two thin lines like that. Let's say there's another frame over here. And then see here, the window would usually be attached to like some wall structure. So let's say let's put another wall here for the window to latch onto. So this is not structural. So maybe this is just to provide like a place for, it provides a space for utilities and a place for your ceiling to latch onto or like bite into. And let's say I just realized this is a toilet. So maybe the window won't go all the way like that. Okay. So that's a wall over there like that. The columns are centered. Okay, like that. And then the wall will be here, and you can see the column behind it. And all of this would be Let me use another color. Let's say orange. This would be the slab. Uh, Let's say orange, orange, orange. Not like this orange. Doesn't stand out. Brighter orange, please. Someone is banging a door. I don't know. It's really bothering. I'm just exaggerating the dip. So this would be concrete, usually. And then you would have your floor tiles on top of the concrete. Let's do something brighter. Floor tiles over there. I think someone's chopping down a tree, something like that. And then you would have another material for your floor finish. It could be timber, it could be vinyl tiles, but usually for houses like these, it's usually timber because it looks good. Okay, so now let's just label it. This is like a wall. In red is your concrete column, RC column, not RC cola, RC column. In green are your ceiling. In pink are your floor finishes. I don't know why I didn't select. My Photoshop is lagging today. FF. And I think that's pretty much it. Also, like this would be called. There's a term for this, but I forgot. I just call them eaves. The materials underneath the eaves, and then your roof gutter. Roof gutter. And of course, the roof is not exposed steel, so you'll have like your roof tiles or like your GI or whatever materials you have over here. And of course, that would also have a waterproof material underneath it, just so it doesn't leak. What else? Anything we're forgetting? Okay, so let's say you would need, what would a house need for utilities? Not so much. But let's say traditionally the dimensions for this would be, let me bring out light blue color here so like really pops. So this would be, as we mentioned before, 2,700. This would be from beam to ceiling about, um, let's say like for this kind of house, like a normal house, let's say average house would be about, let's say 200 to 400. Beam thickness depends on the span, but usually they go for a depth of about, um, let's see, beams. Let's look at this. So that's, I don't know, no, yeah. How about the same as well, 200 to 400, depending on the engineer's requirements and the spacing of the columns and spans. But I think for this house is about this. In section, the beam would look like that. So this would be the 200, the X 400. And this would be the 400. And then you have your reinforce your steel members, like steel, we call that. Your steel bars inside the beam will look like that. And then all your utilities would go in here. And some general notes on the utilities. Let's say this is a toilet, right? Bathroom. So let's say there's a water closet over here. Let's see, water closet. Okay, there's a water closet over here. And let's say there's a shower head over here. And then you would have some kind of like separator. So that would usually be of a concrete material. And then your tiles would go on top of it. Then you would have a glass door of some kind, like over there. And then you would need to include your drains. So let's say we cut directly at the drains. So the drains would be here. Drains would be here. Drains don't go all the way down, like straight down. They go with a P or angled, usually like 45. Let's say we have like we call this an elbow over there. It angles like 45, angles 45 into the probably like the oops, another elbow in down into the septic tank, down into the septic tank over there. And then, so let's try to draw that in 3D. So for toilets, it looks like this. So the toilet is over here. So if you do this in Revit, you're already familiar. So what Revit would ask you to do is like you have your toilet there. You have the, um, I forgot what the technical term for that is. The call out, to- cut out. I forgot the term. Anyway, so the 45 is not in elevation, but it's in like that. And then depending on like the layout, you can move the pipe horizontally. So let's say like this is your XY, your like XY axis. And then you can make it go down vertically. So let's say first it goes like horizontally and then it goes vertically depending on the layout. So that's why this space here, so there would be another ceiling down here, another ceiling down here. That's why this 200 to 400 space is very important so that the engineers can have room. This is for a house. A school would have a bigger sort of ceiling difference, maybe like 400 to 600. So this is so the sanitary engineers, electrical engineers, mechanical engineers have room to locate their different pipes and ducting. So let's say that goes to the ground floor like that. We'd have another wall over here. The walls are smaller in my drawing because they're not load bearing. And then maybe another window over here. What else? Any questions so far? Questions? No questions? Let's see. Typical house section. Wala question yun? Everything is clear? Hello? Bantay bitaw ni gawa sa schematic ug final drawings the same problem sa gyapon manggawas. Yes, hello? Okay, since there doesn't seem to be any questions, I will stop the recording here.
Sir, will you be discussing about the HVAC utilities?
HVAC utilities. Ah, yes. Let me go shift N. Why can't I make a new? For some reason, my SketchUp, my AutoCAD, blah, blah, blah. Photoshop is really lagging. Anyway, so HVAC over here. Let me see. We record again. Start recording. Oh, it's still recording. Thank goodness. It's already almost 30 minutes. We need a visual aid for this. Which one looks good? Ah, this one. Well, that's tiny. Save image as. So just a quick question for bonus points. Does anyone know what HVAC means?
Heat,
Who's this?
heat, ventilation, and air conditioning system, sir.
Yes, that is correct. So who's this?
Dara, sir.
Okay, Dara, another +2 over here. So it's heating, ventilation, and air conditioning system. So if you look at this diagram over here, the machines for providing air conditioning are usually located on top of commercial buildings. So this would be the,
Excuse me, sir.
yes, go ahead.
Kanang wala ka ga-share og
Wala day ka share ang screen. How long has that been happening? Bago lang?
bago ra, sir.
Okay. I was worried na wala ni record to akong gidrawing. Okay, let me close these tabs. Okay. Oh, I have so many windows open. Let's close these. Okay. So what are these called? I think they're called inverters or something. Comprehensive pricing breakdown. HVAC system. Compressors, condensers, and the evaporators. Let's just call them the air conditioners. Okay. So this is an example of a centralized air conditioning layout. So you have your AC units over here. The ones I've seen typically are about, let's say, usually not really cubes, but they're rectangular, like maybe like 600 by 1,200, depending on how much air conditioning you need. And then the ducting for this, similar to the one over here, about 0.6 by 1,000. So similar again, like so if that's pretty much the dimension written over there. The ducting's about, usually if that's the machine, the ducting would be a bit smaller, let's say like 400 by 600. And they would go all over your whole building. And notice the sort of the space between the ceiling and the slab is very apparent. So that's really where the ducting will go. Let's say this is about 600 to 800. Oops, I'm outside of the 600 to 800 mm. And let me see here. What are your questions about the centralized air conditioning system? Typically, yeah, just locate them in the roof and the ducting will go where you need it to go, like in all the different rooms. Bigger rooms would need 2 ducting systems and smaller rooms would only need 1. So what are your questions on this?
It's just the whole kind of general idea lang, sir.
Yeah, okay. So I think we also need, because we have the intake and the like the outtake. So the outtake is like blowing the cold air out, and the intake is like sucking the old air, not the used air in. So typically there would be, I'll just color it in green. So cold air going in, and then used air, I'll color it in red, going out. So that's the general idea. The sort of, what they call that, the exhaust, usually located near, not really super near, but the opposite of near, far away from the outtakes or the vents that are pushing out the cold air, so that you don't have a situation where if you put your exhaust next to your vent, that the cold air will just get sucked out. So that's the reason why there's a distance there. A good distance would probably be about like a meter, maybe 2 meters away, just so you don't have that, just to allow the air to actually circulate in the room. Let's see here, circulate, 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 and go out, something like that. So typically, I think cold air goes down, if that's right, thermodynamics. Let me just quickly open thermodynamics. Dynamics, does cold air movement properties. Images, cold air properties. Move down. Let's see. Living space. I already forgot. I think in general, cold air goes down and it rises as hot air. Yes. Yes, I think that's it. Because that's why we have the vent stack system. Because once a cold air comes in, it absorbs the heat in the room. It becomes hot air, and that's why it exhausts out here. That's why we have the vent stack system arranged like this. And also, speaking of the vent stack system, some of you used a vent stack system where it was not applicable. So the whole reason why how the vent stack system works, if you have a floor plan, let's say you have a floor plan that looks like this. You have your vent stack somewhere here. If your vent stack does not have access to natural ventilation, at least on two sides, then there's no air moving into your vent stack. So let's say um, yellow, 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 yellow. So you have a room here and another room here, and let's say another like room like this. So that's like a dead end hallway type situation. So let's say there's some stairs there. And you say you want to put a vent stack on top of this. The vent stack won't work because there is no natural ventilation going in. It's being blocked by these rooms. So the way to make your vent stack work is to make sure there's an open hallway to at least two sides of your building. Because let me see, let me erase that. Let me erase that. Because you need natural air for the air to move. If there's no air inside your building in the first place, there's nothing for the vent stack to vent. So just like making sure that's clear. So let's say isometric view, 3 floors. Okay, that was basically the HVAC system. Very straightforward. You just need to know the ducting is there and then how it works. You can also apply this sort of to the HVAC system as well. Like if you have your, what's the word? Your outlets, like in the center of the room, for example, center of the room, center of the room, center of the room, like that. And you have your AC units on top of your building like this. The ducting goes to the center of the room like that. Just move that a bit. Going down here, into there, down here, into there. I don't know why it's angled. Let me fix that. Okay. So just that idea of cold air going down, cold air going down, cold air going down. And let's say the vent is like in the center-ish of the room. Let me move my, okay. Make it a little bit bigger. That it really looks like it's in the center of the room. So your, what do you call this? Your exhaust ports, your exhaust for your air conditioning system should be located more on the sides of the building. So sides over there, sides over here, sides over here. It connects back up to the vent like so. And this goes like somewhere over here, somewhere like that. This goes like over here, somewhere like that. So in section, yeah, it'll be a lot clearer in section. The spacing of your outlets and your exhaust should be arranged such that if your outlet is in the center of the room, the cold air has time to like move inside the room to cool the room. And then your exhaust should be like over here, maybe against the wall. or maybe you can still put it in the ceiling, somewhere over there, so they get sucked out as hot air. You see, giving the cold air a chance to move across the room. If it was closer, if your vents were like closer, maybe the circulation of air would only be like that. So that's not good. So this part is not being cooled. So make sure the distance between your exhaust and imports, what do you call this? Air conditioning. What's the word? I'm blanking on the word. Can someone tell me what the word for this thing is? It's on your drawing plans. Let's see. Air supply. Air supply? Air supply ducts. Oh, thank goodness. My brain. If your air supply ducts are in the center of the room, your air return should be in the corner, in the corners. So it allows that whole movement. Okay? That's pretty much it. So let's look at this setup. So I won't be too strict on this because we didn't get to discuss it. So let's see here. The return ducts are in the center of the room and the supply ducts are in the corner. So that's the opposite of what you want to do. It's much more better up here. The supply ducts are in the center of the room and the return ducts are in the sides, in the corners of the room. So hopefully that makes sense. Any questions on that? No questions? Okay. If you can think of a questions, feel like in the middle of the discussion, feel free to ask. What else? What else? Oh yeah, I was gonna do the vent stack. So similarly, in the vent stack, so assuming that your vent has access to natural ventilation on across all of your floors on both sides. Let's say the ventilation comes in here. That's why the arrows are like this, because it's telling you that natural air needs to come in the building before the vent stack to work. I've seen a few works na they put a vent stack in, or maybe it's just one work, sorry. And then there's no windows around around like the floor plan, so the vent stack won't work. So they're just putting in a useless atrium. Okay, so and then as it goes higher, the air becomes hotter. Okay, so usually you would need to have vent stacks in an open hallway, not in the middle of a hallway that's enclosed on 4 sides by a room. So that's basically it. So this could be very applicable to your school. For example, the Archiglobal layout has in section about 4 stories of school like that. 1, 2, 3, 4. Another like wing over here. 1, 2, 3, 4. And they have like balcony, like the hallways over here. 1, 2, 3, 4. It's not so well spaced. Like that. Erase that. Erase that. Like that. Like that. Like that. And then you can have your ceiling, your roof over here. You can have like typical hip roof that you cover with parapets. It looks nice. So the natural atrium in Archiglobal's design really allows for natural ventilation to create a similar vent stack effect, but on a larger scale, like on an open scale. So it goes like that, goes like that, goes like that. Also, it goes the other way. So it goes up there, and also like that. So this is really the principle of cross ventilation, or this is just basic ventilation. Cross ventilation happens when you have 2 hallways that have access or like openings, passageways, whatever. Let's say this is your, not a school, but usually you would find this in a house. So let's say there's a room here, a kitchen over here, a staircase over here, and then you have like what they call this, a like let's say another room over here. So if you have windows in this area, windows in this area, windows in this area, and then windows here like near the door, this could be your main door. This is where cross ventilation occurs. So you have, let's say north is like this. This is why your site analysis is important. Let's say your site is angled like that, meaning your building is very good for kind of admitting natural ventilation because our major winds come from the northwest and the southeast. So this is where your windrows diagram comes in. So with like that, you have wind coming here, crossing over to the other side, and you have another wind like southwest winds coming here, southwest SW, crossing the northwest wind. So northwest, the southwest to southeast, sorry. SE. So this is where cross ventilation occurs. That's why we really prefer open plans for houses, especially in the tropics, because it allows for more natural ventilation. So it doesn't matter any time of the year, because the north wind monsoon happens like for 6 months. Southeast monsoons happens for another 6 months. And that's why throughout the year, your building should be cool. So if your like building orientation does not favor the major winds, your building is not cool and will have to use more air conditioning. Therefore, it uses more electricity. Therefore, it costs more. So that's the idea over here. So you can apply the same principle in your school. So we have the site plan over here. That's already 11:46. Did we get to discuss? We're taking a bit too long. Blah, 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 blah. We need to discuss research and schematic phase preliminary. Okay. We might not have time for those other topics. Okay. Let's see. So north is up. And it's very clear that the science building is trying to orient itself to the major wind. It also probably because of the slope as well. So if you follow the slope, you might be able to gain more access to ventilation because the wind is coming in from this direction. Because north is up. So northwest is here. My voice is going. Northwest is here. Southeast is here. So if this is I think the science building is single loaded. You have hallways on one side only. Then natural ventilation can go into your classrooms very easily. So going in from the northwest during, I think northwest monsoon happens during, I'm not sure actually, one half of the year, and southwest monsoon happens in the other half of the year. If you're in other countries, the direction of the wind changes, but usually there are two major directions, usually. So you just need to like Google your local weather news or like weather information, climate information for that. Okay, so that's how you use the windrows diagram, sort of connecting it with how you use the HVAC system. So in your design, the focus is functionality and budget of 120 million. So you can do a bit of research on that. How much do those buildings in your case study cost? What are the different materials? I think Sir Carl posted like a interesting image, like showing the different prices. Let's go to photos. That's stock Sir Carl's page. Okay. That's all of the Archis stuff. I think I saw it like a year ago almost. Where is that thing? There was a thing about like albums. I think he would be organizing his albums, timeline photos, anything on architecture albums. Akong gi-expose si Sir Carl. Let's see. It's all food. Anyway, there was like an image showing the finishes and price ratio. Finish. Let's see. Construction finish. Price. Philippines. A low cost or rough finish house will be about 15 to 20 per square meter. 15K to 20K per square meter. So rough finish meaning just concrete floors, concrete walls, maybe some paint. Basic finish will be 20 to 25K. So you'll have some floor materials, some wall materials, and elegant finish will be 40 to 60K per square meter. So you can like use this blog the information. Might not be the most accurate, but you can use this as a baseline. So let's see concrete finish, plain concrete finish. Interior. They would look like this. So just plain concrete finish, similar to what you saw in the Safad building. The more expensive will be you have tiles like this, painted walls. This would be around the very easily the 60K per square meter range. But you can make your concrete finish look good. So like this. So this will be probably another 10,000 per square meter with this kind of like cleaned up finish like this, or like it's there's a what, oh, these are tiles actually, so that would cost more. You also see this what do you call this, baseboard. That's also an additional cost. So if you can have, the cheapest would be is similar to what we have in Safad. It's just walls, slab, and then not even the baseboard or like any kind of trim along the corners of the wall and the floor. So that's how you would make your building cost less, but you can also make it look good for less. So something like this, you just clean paint, clean finish. It really depends on like the quality of labor and your visual design as well. You can have something like this, or it's plain concrete, but there's a pattern from the formworks, or something like this. It's timber, so that's expensive. So just imagine that to be concrete, plain concrete, and then just clean, what do you call this? Clean details on the edges of the slab, the stairs, the walls, and the floors. So that's how you make it look good. So you can do research on that. How do you do finishes like this? The other technologies, the solar panels, etc., will also be good. But look for like cost saving measures, something like this. So it's also like timber floor, so that would be expensive. So how do you make reinforced concrete look good? And sort of a general question to those who are attending, do you think reinforced concrete is sustainable as it's being like used today, how it's being harvested, how it's being mined, and how it's being applied? Do you think it's sustainable? Open question to anyone in the class. Am I recording? Oh, that's already been going on for too long. So the answers will be off recording. Stop recording. So anyone